Hi everyone, thanks for joining. Welcome to my presentation for the 2022 CHPC conference. My name is Jode Fourie from the Advanced Engineering Design Group at Nelson Mandela University. My topic is the aerodynamic profiling of a GT3 racing vehicle using both simulation and physical testing techniques as a platform for improving its aerodynamic performance. I'm currently completing my master's in mechanical engineering, and this is the title of my thesis. Firstly, I want to go through the reasoning and the significance behind the project. The CFD methods that I used in my research are not taught at NMU, and so this project pioneered our move into the CFD and aerodynamics sector. This project will open up endless possibilities for future projects utilizing CFD techniques and HPC. HPC is also relatively untouched at NMU, and so as with the CFD methods, we are opening the doors to this for the rest of the university, especially the mechanical engineering department. Now, what makes this project different and somewhat a first of its kind is the solver that we are using to run the simulations. We are using a lattice Boltzmann driven CFD solver from Altair called UltraFluid X. This has not been used in industry to a large degree yet, and so this project will help establish this new way of doing things, pushing the boundaries of the industry. My methodology for the project was as follows. Firstly, we had to 3D scan the vehicle so that a CAD model could be created. This was done using the Creaform Metroscan 3D scanner. Converting the scan to a usable CAD model was where most of the time was spent. After the model was converted, the mesh had to be created. Altair made creating the mesh and setting up the CFD domain a painless exercise, which was refreshing after the excruciating pain of converting the scan to a CAD model. I set up the CFD mesh in Altair Hypermesh and the domain in Altair Virtual Wind Tunnel. I then set up the HPC job script to use 4 GPUs in parallel for solving the simulations. After the job was completed, I used ParaView on the CHPC cluster as my local laptop could not handle the 40 GB dataset generated by the CFD. This was a huge help and a massive boost in efficiency. After the results were extracted, the design changes were made and the process repeated until satisfactory results were achieved. The step shown in yellow is where HPC really came in and saved the day, as a full vehicle analysis took only 4 hours and 10 minutes to solving over 98 million cells. Based on our initial CFD, as well as driver feedback, we identified areas of improvement. The drivers told us that they were experiencing understeer, which means that there is more grip, aka downforce, at the back of the vehicle compared to the front, which creates a clockwise rotation around the center of pressure. So naturally we focused on the front end, specifically the dive planes, as that was an easy place to start. The graph shows a plot of the lift coefficient over the x coordinates of the vehicle, and as you can see, the front peak is much lower than the back peak, showing the imbalance in the vehicle. So the way we are going to fix this is we are going to bring down the front peak to match that of the back peak. My initial thought was not to reinvent the wheel, but rather just to check if it was in the optimal position. I varied the height of the dive plane on the vehicle until the most efficient position was achieved. I measured efficiency in terms of lift over drag and found that by moving the dive plane down 120 millimeters increased efficiency by 1.4%. I then doubled up on dive planes, which boosted my increase in efficiency to 2.2%. I also added a curve at the side to help reduce the spillover of high energy to low energy zones from above to below the dive plane. I then optimized the angle of attack of the rear wing. I found that the original angle of attack of 9 degrees resulted in a large flow separation, and that an angle of 6 degrees was 140% more efficient. The next step in the research is to implement vortex generators on the roof to help reduce the drag. Thanks for watching. I hope you found it interesting.